Great. So today's plan, and by the way, hello everyone, and this is Xiaoyuan. And today's plan is to first introduce our recent VLDB work on range filtered private aggregation on public data, essentially using homomorphic encryption for I guess to build privacy preserving system. And that's gonna be the main work. And also we have a recent work called Agent Beats, which is essentially an open platform for agent evaluation. And if we have time, we'll also briefly go through that, and hopefully this would be a fun journey. So with that, let's first dive into the first work, which is called HADES. Oh, by the way, during the talk, please feel free to just interrupt if you have any questions, or we can also do the QA, whatever works the best. So let's start with a motivating case that sometimes we want to run private query on public data. Let's just say in a medical situation, when a medical researcher wants to learn what's the ratio of patient with a specific disease and what's the effectiveness of them using a certain type of medicine. And essentially, they're going to write this as a SQL query and send it to a database. And the database will return the aggregated result. For example, 64% find it effective, meaning that maybe you should try that medicine. And that will guide the medical practice. However, the problem is for whoever is hosting this database, they're going to learn that this particular doctor is treating a patient with this certain disease just from running this query. And this can leak potentially information from the patient. And similarly, in a financial situation, in a financial scenario, it could be the case that some fairness evaluator is trying to check the loan approval rate in a certain area, and also check that against a certain demographic group. And let's just say if he's pulling this data from a certain company or from, let's just say, a regional database, then again, the database owner is going to learn that, okay, maybe this financial investigator is checking the bias in certain areas so that we need to modify the data or somehow so that the report is not realistic anymore. And we want to prevent that from happening. So the goal here is that can we build a SQL query mechanism that actually hides the sensitive information, essentially the information from the query parameter, and hide this information for the query to a public database. And imagine that you have this aggregation query that is trying to investigate certain I guess business intelligence from this database. And by the way, this is from TPC-H, which is essentially a data set for, I guess, a rich aggregated query. And you have this rich predicates specifying, for example, certain time range, certain quantity, and then you just want to learn the result. What we want to achieve is that from the view of the data provider, all these sensitive parameters are redacted or hidden, but still they'll be able to run all these filters, run these aggregations without actually learning the parameter and also without learning the result. And then after running the query, it will send this back to the analyst or whoever is making the query. And then the analyst is still be able to reconstruct or decrypt that result. And that's going to be the motivation of our work. And let's continue with the problem definition. So formally, we are considering two participants in this scenario. One is called the data provider, who essentially hosts the table, and also an analyst who's interested in writing a query and get the result. We want to support mainly the functionality of aggregation queries, which essentially means count queries, sum queries, average queries, etc. And this is excluding the retrieval query, which will also slightly expand to say why we are excluding that. And in the meantime, we want to support rich predicates. This is actually the part where this is different from a PR, which we will also introduce later. But essentially, we want to support rich predicates, essentially the part in the where clause, and we want to support the equivalence check. We want to support a range query, which is significantly different from previous work, which is also the novel part, and also a Boolean combination between these predicates. And we also want to support other query keywords just to make it convenient for real-world cases. So let's enumerate the system design goal. So first of all, we want this to be a private system. which means that we don't want any leakage from analysts like query parameter. We also want to support the core SQL interface so that it's interoperable with normal systems. We want to have a really simple protocol that is one run between two parties. That means we don't want complicated setup. For example, in MPC, you might have like a non-colluding server setting where you need to ask different parties to host the server for you, or you might need special hardware when you're using a trusted execution environment, or TE. And of course, we also want the system to be efficient, meaning that we don't need to wait for hours just for a single query. And that's something that you would get from like an existing system or previous systems. And also we want to make this like to be scalable, targeting larger database and also somehow support parallel processing. And
just a quick question. So the setting is that you have one analyst, you have one data provider.
Yes.
So you don't want to have multiple data providers. You don't want this collusion assumption. You don't want those things, right?
Great question. So let me actually clarify a little bit. So first of all, it's indeed the case that in the earlier version of this work, we want to support the multiple data provider settings, and later we just decide to simplify. Essentially, I guess the key question here, or to just distinguish against like the MPC setting, is that first of all, there is the case where we have a single data provider, but multiple parties hosting the data for it. For example, imagine a hospital is trusting, let's just say, two cloud companies to host their data for them. And then in this case, you want to secretly share your information with these two clouds. But essentially, the cloud doesn't get any information, but your service is deployed on like a non-colluding server setting. There's also the case of multiple data provider. Imagine two hospitals and with different patient data, but somehow you want to run certain type of query among these data sets. So I guess there's a difference between these two settings, but just to simplify the story, as a first step, in our work, we are targeting like one single data provider, and we are comparing directly with the case where you still have one data provider, but non-colluding server.
Okay.
Hi, Xiaoyuan. So here, I suppose that the data provider would have full access to the plain text of all the data, right?
Yes, and they're in charge of the integrity of those data.
Right. So you trust them for the integrity of the data.
Yes.
Okay.
Great question. Yeah. Any additional questions? Or okay, I'll move on then. So also clarifying a little bit on the privacy guarantee here, that essentially we have a formal definition in the paper, but essentially we are think of it as the following. You want to have two query with different parameter, with only difference in parameter. When this two query is sent to the data provider cannot distinguish which one is which, connecting with like the private parameters. So there are also a few challenges in building such a system. So first of all, there are some existing solutions purely based on homomorphic encryption that actually achieves the simplicity goal. But the problem of them is they are taking like super long to run, even just query on thousands of records. And this is definitely not to the level of like real world deployment. And second, some other solutions, on the other hand, have like complicated setups. For example, you need those like non-colluding servers. This is both like, I guess, like an infrastructure problem as well as like a legal problem that you need to sign contract with like different providers, and or you just need like somehow like trust the hardware for with like TE lines of work. And our observation to improve this is first, we're gonna like first we observe that existing work actually does not optimize towards like a public data provider, which means that essentially you can download the whole database, but you won't do so because the database is large, and also you won't do it for all the clients. And there actually isn't any protocol that covers this setting so far, and we have like a room for optimization there. And also from the research track of private information retrieval or peer, that there have been some like new techniques that can potentially be applied here just for the protocol optimization. And with that, we wrap the problem definition. And next, let's take a look into all the preliminary building blocks that we're using, as well as how our system is orchestrated in a workflow. So essentially, we're going to introduce the idea of like homomorphic encryption in a sort of like a black box function level. We're also gonna cover some characteristic of a specific homomorphic encryption scheme called BFV, and a technique called CRT, which essentially make the protocol efficient. We're gonna explain the use of indicators in peer protocols, and also we're gonna just introduce peer itself.
So just a quick question.
Yes, please.
Are you tied down to a specific homomorphic encryption, or can you just replace with, for example, with some GSW or something?
I see. Great question. I think for this work, we are actually leveraging the property of like batching, at least like the Chinese the CRT batching.
Oh, but that's for
and
efficiency, all right? Or
yeah, that's actually for both for efficiency and also we are actually making a lot of tricks into the vector form of it. If
I
you're
see,
using
okay.
JSW and also the, I guess, potentially the bit representation, it will be a different line of work.
I see. Okay. Okay.
And also, I guess like as like in the earlier like survey phase, we also find some like interesting work of using like the, I guess, scheme change between the like the JSW and also like this kind of, I guess, like FV based.
I see. And like, so in your setting, the analyst is not malicious, right?
What? Sorry.
The data analyst is not malicious. Is honest.
Yeah, they're honest. Yes.
Okay. You just care about the privacy with respect to a malicious data provider.
Yes, that's correct. And also we are not checking, I guess, like consistency across like query runs. That's why we mentioned earlier that the data provider is okay. I can also expand a little bit there because like the talk time is enough. Is sufficient that we earlier also tried to target like I guess like a malicious data provider scenario where you can somehow fix, let's just say like a hash or some sort of like, I guess, like integrity check over the provider side. But we figured that like this would introduce like two potential problems. First is that apparently it's gonna make the protocol super slow, and also the, I guess, like the homomorphic encryption with the ZKP would be like a heavy building block to introduce.
Yeah, sure.
And the second point is essentially this actually also sort of like block the update operation. Essentially you need to claim that somehow your update is benign, and also, I don't know, do a ZK to say that from your old commit and to your new commit, the only thing you change is benign, something like that. And that will sort of like, I guess, like open like a even
so this means what are
Mhm.
So this means what are you actually assuming from the data provider?
Oh, so essentially in this work, we are just assuming they're gonna in charge of like the database and they're gonna provide the honest data, but the protection is gonna be on the privacy side.
Okay, so they are only malicious with respect to privacy. With everything else, they are honest or semi-honest.
So
yeah, I would say like
identical to the classical PIR security model.
Right, sort of, but not the, I guess, like not the symmetric PR, just the normal PR. Yeah, and the reason why we are not targeting like, I guess, symmetrical PR is because, well, if you do average, then there's like an MCP patch that you need to add up. But essentially, I think the
no, because there are like some recent works on PR where like where they do this privacy with a bot, right? Where the data provider could could do some aborting attacks and still violate privacy. Are you considering those sort of aborts or no?
I just want to confirm, like in those systems that you just mentioned, like are there like update operations? Like can the analyst, for example, like do write operation like update?
No.
And in that case, I guess like it's against like a fixed database that is checked by hash or something, or like Merkle tree.
I don't recall, but I mean, yeah, I don't recall how they circumvent that, but I just want so they just have like a slightly more powerful adversary that can also abort now, not just like read queries, respond, and try to violate privacy, but it can also read some queries, you know, do some aborting. But I think it would only make sense if the adversary the data provider adversary changes the database in a certain way and then aborts and tries to find out some query details. But as you're saying, the database is going to be honest no matter what. right? So then maybe
Right.
the attack falls out of your model. Okay.
Yeah, I think like if they are just doing, I guess like if there's like, for example, like during the query, like the data provider just update the database. Also, first of all, I think like the system is probably immune to that simply because like essentially what like you only have one chance in the protocol. We'll also see this later, but essentially you have one chance in the database to change something. You can of course like just deviate from the protocol and then just feed some random data, but even in that case, all the data you are operating on is in the encrypted form. So essentially, you still cannot break the privacy. But of course, you're breaking the integrity by, I don't know, like returning like an invalid like result. But hopefully that solves the problem. And also, there's actually like a super, I guess, like finer grain line across like all the guarantees that this like privacy preserving query system provides. And if we have more time, I can also like dive into a little bit towards our related work section. Yeah, but great question. Thanks. Cool. I'll be moving on then. So first, let's dive into a little bit, I guess, like to the primitive, just for the, I guess, primitive of like homomorphic encryption. Essentially, similar to any other encryption, you have the function of encrypting, which is essentially you take a value, somehow hide it into like an unreadable value, and you also have the decryption, which recovers this result. The part of homomorphism is that you can actually operate between different encrypted values and also like in the encrypted value and the plain text values. For example, if you take the look at the line here, you will see that you can add like a plain text value to an encrypted form and then obtain the result also in the encrypted form. And such operation is fully homomorphic when you can do multiplications between also encrypted values. And that actually guarantees you, well, Turing complete in some sense, but also there is this like noise growth problem which limits your circuit size, but I won't dive into the details there. The takeaway here is probably you can operate under the encryption, but in a limited utility. So there are certain schemes that can make this that can implement this think of it as interface. Essentially, the one we are gonna pick from this work is called BFV, and it's depending on like the space of polynomial rings. I guess I won't dive into too many details, but there is one thing that is particularly important, which is there is this like CR Chinese remainder theorem batching scheme, which actually allows you to, instead of processing in the domain of integers, you can process things in the domain of vectors of integers. And also, when the multiplication in this case become element-wise multiplication, meaning that you have dot product in some sense. And also, there is this special operation called rotation, which we'll also mention a little bit, which is when you're encrypting this vector of 0, 1, 2, 3, whatever, you have the ability or have this operation that you can change the position of certain element in this vector. And the way you do it is by shifting the whole thing, either swapping like the first and second part, which is essentially 2 row, or just like rotate it towards one direction and change the offset. And of course, the advantage of this CRT batching is that you will have a much higher per record efficiency for processing, but the drawback is that it will reduce the bit width for each of the elements in the vector. And we'll see how this accommodates into the real system when we do the optimizations. And next, we're going to introduce a little bit about how such like homomorphic encryption building block can be used in a privacy-preserving system, such as the task of like private information retrieval. Essentially, think of the task as you want to, given a list, you want to retrieve a certain element, but without letting the server knowing which element you choose. And the way you do it is based on homomorphic encryption, is that you can construct this vector of 0 and 1. If you want to just retrieve one value, you can just keep one encryption of 1 and all the rest set to 0. And then you can do essentially do a element-wise multiplication with the second vector. Then you get the selected version. And do keep in mind that from the server perspective, all the encrypted values are not visible, so that it actually doesn't know which one you select. and then you can just retrieve this back to your own and decrypt it to get like which one to select. And also with the encryption of 0 and 1s, which is essentially the indicator vectors, you can also perform Boolean operations of and or simply via doing multiplication or doing like addition, subtraction, essentially like the homomorphic operations that we mentioned earlier. And of course, you can also do OR operation. And such building block is actually commonly seen in computationally, I guess, PR protocols. We similarly in this work, we're also gonna use like a similar protocol for the core reprocessing. And I guess before I dive into the workflow, any questions for the preliminaries that we can quickly iterate through, because there are some relevant part later as well. Okay, I'll be moving on then. So with these building blocks, the way we construct our system is to somehow encrypt all the secret values in the query in the homomorphically encrypted form. And then we're gonna send this like encrypted parameters along with like the query skeleton, which is essentially the template here, together both to the data provider, which hosts the tables. And then we're gonna do indicator calculation, which essentially give us the encryption for 0 and 1 for each predicate. We're gonna then perform Boolean circuit evaluation based on like the template here to figure out which record got finally selected, and then run the aggregation by either just adding the indicator itself or adding like the result after the multiplication, and get the final result also in the encrypted form. Then we send the form back to the analyst to decrypt and then get the final result. Yes.
So yeah, sorry. I think you went a bit too fast here.
Okay.
So the query encryption, you have the skeleton of the query. The
Yes.
exact parameters are encrypted as you have shown there.
Yes.
So the indicator calculation is done by the data provider.
Yes.
Right?
Everything,
So
I
how
guess,
does
right side of this is.
how does the data provider do this indicator calculation?
Great question. That's gonna be the, I guess, like the core protocol we're gonna construct in the next section. But essentially, I guess like here's a I guess like a
okay. So this is still in a workflow.
Yes.
Okay.
We're gonna explain, I guess, two building blocks. One for the second step and one for the fourth step later, and also how to make them efficient.
Okay.
Great.
Just a question, maybe a dummy question. Will there be any like leaks because of the computational like the computing time, where the computing time actually leak information? For example, maybe.
Great question.
Yeah.
Oh yeah, okay. I guess I'll pick an answer. So the timing, I guess like you're probably worried about like timing side channel. That in our protocol, the processing time is dependent on two factors. One is the query template here, which is public above here, and the second is the database size. So essentially, the analyst can learn how large the database is, which is not a problem because this is a public database setting. Well, in the meantime, the data provider still cannot learn anything because he already know the template, but the query parameter here actually does not influence the computing time, if that's the word.
Right. But can the indicator calculation time varies with the row distributions and stuff? Like, for example, encode 1, right, is taking maybe a bit longer than encode 0, just because like how. Yeah, I mean,
it's a agnostic.
Okay.
Yeah, I guess like that's actually one thing that we definitely need to make sure in our protocol, which is if you just do computation among like different like encrypted values, it's the same time. I mean, like the time consumption will be the same. Yeah.
Is that just assumption you have, or you actually
And
yeah,
yes,
sure,
it is the same
okay.
because essentially you are processing across like random values, and
Okay,
you can think of it as the op count is the same.
right.
Yeah, and also there isn't a caching problem that if you have same value or something, we make sure that doesn't happen.
Okay. Okay,
Yeah.
cool. Thank you.
No problem. Great question. Cool. And then we're gonna move on to the proto design, which essentially solves the, I guess, like the earlier concern on like how this is achieved and also how the aggregation is achieved. So first, let's so essentially we're gonna go through the following building block. First, how we do equality checks. And we're gonna start from like smaller bits of values and then expand it to more bits. And also we're gonna cover how we do range filters, which is essentially one of the novelty in the paper that doesn't cover by the previous work. And also we're gonna go through like aggregations. And if you just wanna do Boolean combination between these like different predicates, we already mentioned that in the earlier phase where we talk about, I guess, indicator vectors. So the idea here is actually pretty simple. Oh yes, please.
Sir, I'm just thinking of, I'm a bit slow in thinking about the previous one for the flow, and I was thinking about what Li was saying in the protocol flow for. So if we go back to the flow, you had this nice figure to show ESD1. So my understanding is we are saying that the timing is identical, which is in terms of the result for either encrypting 0 or 1, right? So there isn't much difference. However, later there needs to be an aggregation for the result from index, right? Let's say if I'm a malicious data provider, I will be able to separate the database into different segments and then performing the aggregation. And that leaks some information because some segments may have more data to be aggregated, and some segments may have, for example, in the extreme case, 0 data to be aggregated. So there will be a difference in terms of depending on how many items that are actually the encryption of 1, then the computational time could be differentiated, in a way that it potentially is a linear kind of increase depending on number of recalls. Will that also release some side channel information about the computation?
I think that won't happen because for encryption 0, you still do the computation regardlessly, right?
Right, exactly. It's gonna be a fixed procedure, right? So we also have like a slides to show this. And by the way, this is a great concern that actually the data provider never learns like when, got really a lot of like animations. But essentially, they do the aggregation in a fixed procedure that like the steps of operations are the fixed, and they don't actually know which records are selected. So they're gonna process across like the whole database anyway without any segmentation.
I see. So what you are saying is that the computational overhead here is O(n), where n is the number of recalls in a database anyway, rather than m, where m is the number of matching recalls.
Yes, and that's actually like I guess like under this assumption is a lower bound, because if you are not touching all the record, then the record you are not touching essentially leaks the information about like the predicates. So essentially I think this is also like a fundamental problem with the PR. Like I guess in comparison with like ORAM where you actually know where to go. I think it's sort of like a fundamental problem. But hopefully this clarifies.
Thank you.
Great. Cool. In that case, I'll move on with the, I guess, like the protocol that so essentially let's I guess like clarify the smaller scope problem here a little bit, that what we want to do is to compare actually a plain text with a ciphertext. The plain text being the data provider knows about its like own database record, and the ciphertext being the hidden predicate. And we like in a concrete case, think about we have the encrypted form of some value. We have a database record of 41, and we want to learn if these two are equal or not. If it's equal, I get the encryption of 1. If it's not equal, I got the encryption of 0. And this is the problem. So there is the existing solution of just doing bitwise comparison and build a circuit out of that. And of course, there are problems. First being it's super slow, and second, also you need to somehow represent your data also in the bit form, which actually wastes a lot of space. And we are here proposing like a new trivial solution, which is essentially just indexing. And it might sound stupid in the first place, but let me try to explain how that could be made efficient. So first, like the protocol goes as the following. The client is gonna send this vector of 256 values covering the 8-bit domain. Each of them is gonna be either encryption of 0 or encryption of 1. And then the server is gonna return with the correct index return which like encryption you're gonna, I guess, return like that specific encryption. And the advantage is that this actually never touch anything related to like homomorphic encryption and no homomorphic operation. So it's super fast. Like essentially you are just getting the like one indexing and done. However, the problem is that think of expanding this into like 16 bits or even 32 bits. Essentially, you're gonna send 2 to the 32 records back in actually encrypted values to the data provider, and that's a huge communication cost which we cannot tolerate.
So just a quick understanding. So
yes.
you have 8 bits, which is like the parameter that the data, the analyst's parameter, right, which he encrypts,
yes.
is you're considering it to be 8 bits.
Yes, like a predicate with 8-bit equality check. Like
okay.
I can only operate on int 8.
Okay, so he essentially encrypts all possible values for this, and
Yes.
how is this selection done at the provider's end? This is something that
there's no selection yet. I think this is just help the client to prepare for that predicate parameter, I think, right?
Yeah. The vector construction is purely done by the client side. And just to answer the question of how the server will choose from this, essentially the server gets a list of 256 values. And it just indexes the corresponding one without even knowing what is this value, and then just throw it back. I know this sounds like stupid, like in the first round, but later we'll find that this actually is more efficient than the. If you do this carefully, you will make it more efficient than let's just say like a bitwise solution.
I see. Okay, so let me understand this. So so you have in the example above, you have encryption of 42, right? Which I assume
Yes.
is 42 is the parameter that the client is interested in.
Right.
And what is this question mark equals to 41? This I didn't understand.
This is just to define the problem that essentially the protocol, the challenge to design the protocol here is you have an encryption of whatever value that is 8-bit. You have a plain text of 8 bits. You want to have a protocol which generates encryption for 0 or 1 based on whether the value are equal.
Okay. So the encryption of 0 means that it's indicating it's not equal. That's what.
Not equal. Yes, it's an indicator of whether the equality holds.
Okay. I see. Okay.
And yeah, let me just also route back a little bit just to make sure this is clear. That so essentially check here, like you want to have like a ship date that is later than like 1994. So this is later than 1994. This is later than 1994. So we got encryption of 1 here.
I see.
Essentially, we are doing this step.
Okay, so that's what you want. Okay, that's what you want. Okay.
Yes, and of course, this is for
this is clearly not 8 bits.
Yes. So we're gonna also cover how that is done later. But it's actually the same protocol, so you can probably imagine. But still, let me wait. Let me go through this. So yeah, essentially the challenge here is that because you are sending like 2 to the 8 values, the communication is kind of burden. For example, if you're doing like 32 bits, then you need to send 2 to 32 values, which is problematic, right? And the solution here is actually super simple. Because we already support AND operation, so the idea is that you check 8 bits every time. And you only need to provide like 4 ciphertexts with like 256 slots, and then that shall do it. Like as a quick example, you can just think of this like chopping it into like 8-bit chunks, and then you do 3 AND operation and the problem solved.
Yeah, so basically you just want to save encoding space, right?
Yes. And also, I guess like mainly like saving the homomorphic operations. we'll also see that like in the how we can optimize this protocol. This is a basic idea. We'll later, the challenge here, by the way, just going forward a little bit, that the challenge is, okay, I actually don't have time to dive into the details, but essentially the challenge is how you can make this happen in the vector space rather than just like the plain text space. And we're going to cover that slightly later. And then for random query, it's the same story. We want to know if this like a plain text value 42 is within a certain range. And we want to generate yield like encryption 1 or 0 based on this. And again, we're going to send 256 value. Just mark all the things like within the range to be encryption 1 and all the others to encryption 0. And you do indexing and return the value. And again, here, the challenge is how to process the batching version. And you can also imagine extending this to 32-bit is essentially trying to break this down to like further like more, I guess, like and or operations like in the like smaller chunks of data. Essentially yet another like circuit, if you think about it. So you can think of our solution as a combination between not the bitwise circuit, but like a 8-bit building block wise circuit plus the indexing procedure. And later we find that this actually achieved the best performance compared with like two, I guess, extreme. One is the bitwise version and the other is like just doing 2 to the 32 communication. And then there's also like another challenge, which is the aggregation. And please do keep in mind that like we are actually processing data in general in vectors, so that if you got this like response of like 3 ones occupying different slots, you still want to add them together. Especially when you have multiple ciphertexts, you want to add everything into one ciphertext before returning just to save the communication. And the approach to calculate this is also simple, just rotate it 8 times and then add things up. But of course, this is not the most efficient solution, and we'll see how this can also be optimized.
So why is this aggregation useful? So what does it mean to have like 3 ones? It means that three values in the database are supposed to be the correct responses, right?
Yes. Imagine that you have a database with 8 records, and then you have a predicate which selects 3 of them, and your query is a count query. Then you just want to get like how many records are selected. Then you need to somehow add it up and then return.
So this is about record, like the number of satisfying records.
Right, like it's a count query.
Okay. Oh, that's what you mean
like
by aggregation.
Yes.
Okay, I see.
And there is a slight problem with the sum operation, but it's also like I guess like the easy version is that instead of like just adding the original indicator vector, you can do multiplication first to retrieve the record and then add things up. And the problem here is that there's going to be overflows. In practice, the CRT batching scheme we are using, while providing a lot of, I guess, like slots in the vector space, essentially like 2 to the 14 records within one ciphertext, it actually only support like 17 bits for each value to be reported. So if your addition is overflowing by this like I guess like bits number, then you can actually never recover the correct value. And the solution here is actually also quite simple. That instead of adding the original value, you use a octave representation, which essentially allow you to do like 2 to the 14 times like 2 to the 3, which is still within like 17 bits. And then you just get the result back later. Cool. I also have, I guess, like an example, but due to the time reason, I won't be walking through it. Yeah, I guess given that we'll still have like 10 minutes or so, I'll just, I guess, dive into the more interesting part, which is essentially how this protocol can be made efficient. And just to recall, here is another round of formalization of like our building block, which is given like instead of like saying just 0 and 1, this time we formalize it as like a given mapping that is like in this like encrypted form. What we want to do is to apply this mapping from its like a value domain to the target value. And no worries, I'll also walk through this with an example later. But essentially, this is a new building block we're going to be using for both the equivalence check and the range filters. And here we go. I guess most like the core contribution for this paper, which is how can we make this mapping to be efficient in the vector space. So let's reiterate the goal a little bit that we want to, this is our original database, which have the record of like 2 to the 2 in this case, just to be simple. And our goal is to map 0 to F0, 1 to F1, and here again 1 to F1, and then like just convert this vector to the right-hand side vector. And the data, the predicate is actually encrypted in this value, in this form of F. Essentially in the equivalence check, in the case of equivalence check, just think of it as 0001 or 0010. And in the range query, you can think of it as 0110. But in general, replace this F with whatever predicate you want to calculate. And the protocol goes as the following. So the first step, you rotate all the mappings to make it fill the whole vector slots. And the second step, you pre-calculate all the different types of rotations for in this case 2 to the 2 types, and then just cache them for later usage. And then you do index calculation by trying to figure out if I want to put F0 into the first location, which pre-computed ciphertext should I use? And in this case, if you want to use this one at the first location, we're gonna use we see that CTF0 have the same value, so we put the indicator of plain text 1 here. And then for the second slot, we want F1 to occupy here. So again, we will have a indicator 1 here. And similarly, for the third slot, we want to have a F1 to be put here. So we find that F3 have this, and we set this to be 1. And after calculating this plain text values for picking which record to be added to the final, encrypted list, we do the multiplication and add things up so that we get the right-hand side. And just to jump into the conclusion, this actually saves a lot of time, 98% of the time, if you just compare with just doing it in a naive way. And this is the major saving from this work. And also we have some other approach to optimize the aggregation, which I won't expand for this talk. And let's see some experiment results. So we're working with the TPCH benchmark here, which is a commonly used database benchmark for aggregation. And we're comparing some previous work also for certain types of queries. It's actually 3 queries here. And just from the latency comparison, and by the way, we are assuming similar, actually slightly weaker machine specs. But what we get is we can reduce the 14 hours or 27 hours of processing time for 1 million record to be within a minute. Just we are using the new protocol. And we are also trying to profile our earlier workflow a little bit, and we find that for different stages, depending on how your what your query look like, you may have different bottleneck stages, and also based on depending on different scale of the data set, the saving from the rotation caching will also be more significant. We also do a profiling with different numbers of cores to see the scaling attribute of this system, and the result is that the utilization rate per core is not decreased until something like 2 to the 4 cores. And also this is assuming this is on the same machine. If you just scale it with the multiple machines, it's still possible. You can just run the protocol multiple times with multiple instances. And also we saw that there is certain step which is actually not that time consuming, but with the increase of the core numbers, it cannot be further saved, which is potentially the bottleneck. We also see that we also do micro benchmark on our building block, especially the optimization that we just mentioned. And we see that, first of all, if you look at horizontally, you see very good scaling features that if you have more bits, the time just doubles, is almost linear. And if you're looking vertically, you see that our solution achieved the best for most of the cases. And we also benchmark our, aggregation, which also shows that this constant saving of 8 times, which since we don't mention the the details about the details about the protocol, we won't dive into there. And with that, the later part is a bit rushed, but hopefully that covers the idea of like the HADES paper. And next, I'm gonna either pause for some questions or just quickly go through our new project on agent-based. Lee, what do you think will be the best?
Well, I'm flexible. No, anyone has any more questions regarding the previous part?
No.
No?
Okay, in that case, maybe I'll just do a quick, I guess, 2 or 3 minutes, like brief overview, brief go through for our recent work. And by the way, here, like the flavor is like, I would say like much different. It's still targeting, I guess, like security related research, but this time we have LLM and agents. Our observation is that there are many agentic libraries, packages, and also there are many standards, many proposed evaluations, but none of them are standardized. And we identified 3 core problems from this like other research for agent-based. First is the lack of standardization. Essentially, for your agent to be run in different like environment. I'm not. By the way, I'm not saying like just replacing the model. Here, I mean like replace the whole agentic system. That can potentially have like web browsing, like a tool calling, like other abilities. If you just want to adapt that agent to all the like different agent evaluation, you for each benchmark you need to write some code just to make that happen. And also, there's a limit in openness that you cannot just access someone else's agent in the standard format or like environment. Imagine that for a dataset or for models, you have Hugging Face, but for agent, you have nothing. And also, you have low reproducibility, meaning that like you can only just pick up someone's like a random GitHub repo and then just run it. You don't even know like you are using the same backend, you are using the same LLM endpoint, and this is painful. So what we propose is to build a new platform which supports this like standardization, openness, reproducibility, while also being easy to use, meaning that we can just instantiate one file, instantiate your agent with one file and connect it with CLI. Think of it as like when you run against like a certain benchmark, you just import a package, make sure your agent is compatible with a standard called A2A from Google. Make sure that your agent operates under that standard, and then drop the API and then get the evaluation result. And also, we already have done like rich integrations into web agents, coding agents, prompt injection scenarios, etc. Just to make sure that if you have an A2A agent ready, you can test a lot of things. And the target use case is that you can evaluate your agents, compete with others with a ranking leaderboard. You can contribute new benchmarks or environment via also this like standard format of also putting them as a new agent to monitor the, think of them as like serving as a judge. And also you can collaborate, letting others to test your agent and also improve based on the detailed insight from the evaluation. We are supporting 2 evaluation modes, one for the single agent benchmarking mode and the other also the multi-agent. When you have multiple agents hosted by the platform, you can just incorporate them into a shared session for like a richer evaluation. Think of them as for example, there's this recent research on werewolf game conducted by like different, I guess like LLMs and like just imagine adapting that also to such like a platform, and you can have like different participants with ranking. And there are some, I guess, like concept where we're building here. For example, like we have agent-based agent, we have different types of agents. Some are in charge of benchmarking, the others are in charge of participating. We also have a new concept called assessment, which is essentially an abstract for just building new benchmarks. And we are providing some basic features. For example, you can have an agent registry that you can put your agent on. You have a controller that tells others to reset your agent where something wrong happened. And also, there are some like, I guess, like tracing observability related functionality. So for more information, I would highly recommend to just check out our, I guess, webpage on the right upper corner here, or join our Slack channel, and we are happy to share more. But essentially, that's about it. Thank you so much for your attention for 1 hour, and yeah, happy to take questions.